Being here. As you all clearly know, we had several folks from Central New York who participated in the ARPA-E Innovation Summit now 2 weeks ago. And also Tim LaBreche last week was, you know if this is in the call. Tim was at Berkeley and visited Lawrence Berkeley National Lab. Right? Will you be speaking about that?
I will be, yes.
That's a good thing.
That's a good thing.
Again, I'm pleased to welcome you to this monthly Research and Technology Forum. I'm looking forward to the presentations by Chetna and Tim, James and Ryan. And Ryan?
No, just one.
Just one Ryan.
Ryan squared.
So, Chetna's only dissolved. Chetna, Chianese.
Thanks.
Chianese.
We're Italian. Thanks all for coming. So we wanted to mainly talk to you about some of the cool science technology things that we found at the summit. So some of the stuff you'll be seeing that wasn't actually seen at the summit, but we only got some highlights. So we'll talk to you a little bit about that generally. So what is the ARPA-E Energy Innovation Summit? It's a ARPA-E is a division of the U.S. Department of Energy, and starting in 2009, they decided they were going to have this big meeting with lots of great companies and researchers talking about technology. So this is from actually 2014, but they had over 2,100 attendees, about 120 speakers, lots of panels, great networking sessions, and this large exhibition where the 280 transformational technologies were highlighted. So a lot of what we're going to talk to you today about is the technologies that we saw in the showcase and what the highlights were from that. So here's a little video about what is ARPA-E. Whoops.
ARPA-E plays an important role in the U.S. energy innovation ecosystem.
We're all here to solve the three problems that Congress told us to solve. Weaning ourselves off of foreign energy sources, increasing energy efficiency in the U.S., and it's reducing emissions related to energy use.
When we talk about changing what's possible, it's not just the technologies. It's actually the approach to research, and it's the approach to engaging the broad energy community in moving things from ARPA-E onto the next part of the development cycle of energy technologies.
We're investing in the best people, the best small companies, and the best ideas to bring entirely new energy technologies to market.
The best thing that we can have is a suite of different options because it's risky and it's hard, and we're not foolish enough to think that we can prescribe the solution up front.
Our role as ARPA-E is to fund early stage technology development before the private sector is willing to get involved. We're trying to remove enough of the technical risk that the private sector and industry can pick it up and run with it.
ARPA-E is not about just identifying some big new problem. I think the problems in energy are pretty well known. ARPA-E's unique piece of this is framing the problem in a way that has not been framed before. And therefore you bring different people to the table with different eyes on the solution.
You're trying to engage people that are really brave and pushing them to get off their comfort zone and really thinking about the problems in a very innovative way. It's something that is very distinctive about us as an industry.
We're asking them to cross disciplinary boundaries to really come up with new approaches to difficult problems in energy.
We would run into folks who would stop us and say, you know, I've been working on this field of chemistry for 20 years, and I never knew that my work could be so important for the energy problem.
We actually go on site with all of our performers multiple times a year. And we spend a substantial amount of time with the research teams trying to brainstorm with them how they might solve their problem. It's a real true partnership.
That won't start out with you and your team, but it goes beyond that.
We ask questions like, let's say you're wildly successful. How much could you imagine this technology costing? How cheap could it be? Is it going to be good enough to actually move the needle based on what we have? And we look at each part of the life cycle through the lens of, if it works, will it matter?
Just because some of them will likely not be successful doesn't mean it's not worth going for it. And a lot of those things that might not be the home runs still teach us a lot about how to ask the next question.
I think the impact that we make as an agency goes way beyond developing technologies and commercializing them, but also educating and developing a community that can be leveraged again and again.
Our success really depends on engaging the broad community in what's possible and having them believe that it's plausible that this can move all the way to market and change things for future generations.
So as I was saying, ARPA-E, it's the Advanced Research Projects Agency for Energy. It's like DARPA, but for energy. And so you've seen in DARPA, they have those like robots that are supposed to be able to just like run on treadmills. So that's the energy version. We don't have robots here as much, but they have some nice technologies. So what is the mission of ARPA-E? They are catalyzing transformational high-impact energy technologies. The overall goal is to reduce imports, improve efficiency, and reduce emissions, and that will lead to America's national security, economic security, energy security, and have the U.S. be a technological leader. So a little bit of the history. The agency was authorized in 2007 from the American Competes legislation, but it got the first bit of funding through the Stimulus Act, where they got $400 million to establish the agency. And as of last year, they had invested $900 million in projects. There were 362 at that time. You can see the breakdown that a lot of them go to universities, 35%, but a lot, 37%, were going to small businesses. Now, some of these were university startups, but some of them could be a small company like SBB, for example, that maybe had a cutting-edge technology, but they weren't really sure how to take it to the next level. And then large businesses. So we work with the United Technologies Research Center, for example. They're considered a large business because they're a branch of UCC. And they make up about 20%. And the national labs, which tend to get a lot of permanent energy funding, aren't really participating so much. So universities and small businesses are really the core of the funding. Now, to show how they've been successful, they took 22 of the projects that had managed to gain a lot of venture capital funding, and those 22 companies have seen $625 million in private sector funding. I think there are one or two companies in there that each got like $100 million, so that's where a lot of it comes from. But these are companies that have really cutting-edge technology and now have seen it going to industry and going to the market. 24 new companies were formed, primarily from the university. They had some spin-outs there, and then a lot of them have gone on to see funding from other agencies. They divide their programs up into transportation, stationary, and then a mix of the two. And then they really like their acronyms. I think that they spend a lot of time thinking of acronyms. So like BEST has to do with battery technologies, like batteries for energy efficient storage. So they have that. They have biofuels. This is using fuels to sunlight, or sunlight to fuels. Then they do, solar technologies. They do a lot of stuff with the grid. So things like transformers. New cutting-edge transformers is not really that interesting to a lot of people, but it can make a big difference in the technology. They do carbon capture because they really look at all areas of energy and not just renewables. They have this metals program which finds ways to make lightweight metals more effectively. So aluminum. How can we get aluminum to be really deployed, particularly for vehicles? So how do you get in, so they create new learning curves through those programs. They like to say they take a lot of shots on goal. So the idea is that if we have one program that has 10 projects under it, a lot of them will not work. You start out with a very high cost for the amount of performance they can get to, and a lot of them will fail. But in the end, they're going to beat the existing technology, which a lot of times you just kind of slowly bring down the cost curve. They want to dramatically bring down the cost curve and get to a technology that will get to market. So although a lot of the stuff that they're trying won't work, it's going to be those 10, 20% that really work that are going to transform the market. And then what makes an ARPA-E project? I think in the video you saw, if it works, will it matter? So it has to have a high impact, and it has to be in the mission areas of energy. it has to be transformative. So it can't just be like, oh, we're going to take the existing solar technology and make it 5% better. They're looking for things that make it 20, 30% better. Some really cutting edge science and technology. And the idea that you're bridging, you're not just doing basic science or applied science, you're really figuring out how you can take it to market. And the teams, they really are the best in class researchers in their fields. And then cross-disciplinary. So in addition to having mechanical engineers, you'll have electrical engineers and design people and chemists on one project. So the idea is to really take advantage of all the disciplines. When they start a new program, they identify the white space, they create this program, and they're actively involved in managing it. We said that they visit the programs all the time to really make sure that they're learning lessons from everyone. And there's a big focus on technology and market. So in your average applied research project, you're not really going to be doing a lot of techno-economic analysis, and you're required to do that for ARPAE projects. So I have this cool widget, and you have to figure out now how much it would cost if you wanted to manufacture now and how much you can bring down that cost curve. And they help you engage with stakeholders in your field. If you're a biofuels project, they connect you to the people in the biofuels industry to see what they want, how they can use your technology. If you're interested in getting involved in ARPA-E technologies, there are specific program calls out there. So those funny acronyms. You can apply to be in a specific program once those come out, but those are very specialized. So, for example, Professor Gliebe here got an award for one that was on local thermal comforts. The idea is that personal ventilation. But Professor Gliebe has been doing this for years and has a lot of knowledge in that area, so he was well suited to that. If you have a crazy idea and you think it will fit in the areas, that's great. But those are pretty specific. There's an open funding opportunity every 3 years. They say, throw us your craziest ideas. They get thousands of concept papers where people, any idea. They really, in the beginning, they wanted the guy in the garage who had a crazy idea. And some of them have worked out and some of them have not. But, the idea of using kites to capture the wind energy more effectively to create electricity, those come out of this open solicitation. Unfortunately, that just closed on Friday, so you can't enter if you haven't already. So look for that in 3 years. And then they do small business innovation and research. I know some of you have been involved in that. And sometimes they just do any topic, but most of the time it's a subset of a program. So it's a little hard to get in if you're not in the specialized programs. So what do we think is going to come out next? We sat in on what they did program pitches, so the people who run the office came in and said, here's what I'm thinking about. We know that there's likely to be one on optimization of electricity transmission networks to facilitate renewables integration. So this is about optimal power flow sorry, let me look at my notes here. It's about finding steady-state operation points which minimize generation costs. So how do we balance load control and how do we balance the demand level with the set points and find the optimal scheduling? They're talking about this being some kind of prize competition, so it's pretty fun. Could advanced technologies get us to yes for efficiency upgrades of single pane windows? So this is a program run by Eric Schiff out of the SU Physics Department. He has taken a program director position at ARPAE for a few years and came up with this idea that if we can take all the single pane windows, primarily in the Northeast and the Midwest, and convert them to double pane efficiency cheaply, easily, then we can have a huge dent on energy savings. So yeah, it's really single pane windows getting double pane efficiency. I think the cost was like $6 a square foot. So ridiculously cheaper than you could do now with good technologies. You can do those cheap window films, but those don't get to the efficiency that they want. You can do professional installations, but that's really expensive. So what can you do that an average homeowner can put in their own house, but really change the cost curve? I went to this workshop. They talked a lot about aerogels and other kinds of sprays as the easiest thing. So if you have a crazy idea on how you can make a single pane window much more efficient and cheaply, this will probably be coming out in a few months. There's 3 ideas which are in the stage where it's just ideas now. They'll probably run a workshop on that, and we know these people, we pay attention to the workshop, so if you have an interest in any of these 3 ideas, you can see me and I'll let you know when the workshops are out. Advanced technology engines and powertrains, what are the limits to efficiency? This is focused on light-duty engines. There's an idea of can we have better catalysis without better catalysts? So those of you who know the catalyst field, a lot of the really good performing catalysts are expensive. So how can we take some cheap material and make it much more efficient through some more physical means, and not just talking about pressure changes. I'm talking about a lot of physical changes to the catalyst itself. He was kind of fuzzy on the details, but he's just thinking of this, so the workshop will be coming out soon. And then a unified transportation and electricity infrastructure. So we've talked a lot about how to use, people have the ideas that they can use hybrids for demand control a little bit. So if you plug in your car and you can charge it at 2 a.m., but at 7 p.m. you're actually putting electricity into the grid because you've stored it in your vehicle. That seems to be what this idea is going to be about. So, things that other people have done, but they're trying to take another spin at it. So I mentioned we went, so we had a booth there, Syracuse Center of Excellence booth. So we brought James Shomar from Solstice Power. He's going to talk in it a little bit. Professor Jean-Min An came with us, and he brought 2 students, Ryan Strike and Ryan Falkenstein-Smith. And Ryan Falkenstein-Smith is going to talk a little bit about his experience. And then Tim and I went. So we had a good time. We talked to a lot of people. People were interested in what Syracuse is doing in the in energy fields. A lot of the people we knew already just came and talked to us. So we had some people from NYSERDA stop by, other startups in the area. So we're really trying to figure out how to work together with some of the local companies and some of the other institutions in New York. So some of the technologies we found, they had some pretty cool stuff there. We saw SLIPS, which is slippery liquid infused porous surfaces. So this is technology invented at Harvard in 2010, and they actually won an R&D 100 award a couple years after that. So the idea is that they have structured, functionalized surfaces. This isn't really the best representation of what they do now. It's more kind of amorphous rather than really structured here. But then they add a lubricating layer, and then the whatever is on the surface can just flow right off of it. It transforms the surface of solid material into a microscopically thin. It's very thin, an ultra smooth sea of lubricant. So it's omniphobic, it's highly repellent, it's transparent, scratch resistant, self-repair, self-cleaning, and it stands up to extreme environmental conditions. They did a little pitch about their business, and it came in second. And they're supported by some local New York State companies. So if you guys know Pat Sapinski, she is supporting this company, some of her connections. I think that they're starting to do a Series A round. So just some of the examples here, you can see this is some biofouling, how clean the slip surface is. And then it resists icing. So this is just bare aluminum, and then this is where it has slips applied. And you can see that the frosting is not seen. So the idea is you can use it on refrigeration coils. You can use it in pipelines to reduce some friction so it can flow through the pipelines quicker. You can use it on optical surfaces. So the idea is put on goggles, ski goggles, and you can just have everything melt off of that. So here's a little video there. They had a lot of examples like.
Ed wants to see the one.
I saw a presentation about the ketchup bottle.
Yeah, they had a ketchup bottle. They had a video of the ketchup bottle the
Yes.
same way.
In fact, they're working with some people who package things like this. So instead of shaking ketchup,
Yeah, food packaging. So they have. I didn't show that part of the video. It's like a 3-minute long video where they just show all of these applications. So, you know, the idea that you can have this platform technology and use it in lots of industries is interesting. And bringing up Thermalist, they're also locally affiliated. They're based out of the Advanced Energy Research Center out of Stony Brook, and they've been coming to the ARPA-E Summit for a few years now. They are a thermally driven heat pump for heating, cooling, and hot water in one device with no refrigerant. That's their sales pitch. So the idea is that they think that they can provide 30 to 50% reduction in fuel consumption through this thermally driven compressorless heat pump. And they have a little video as well.
Okay, so good morning. It's Friday, September 12th. We're here in our main ARPA facility, and we're here trying to get our Thermalist device into the test cell so we can have our initial testing phase and see if we can move some heat. That's our goal. Our goal is to be a heat pump.
This is a very exciting stage of the program. We've been several months both designing various iterations until we came to a design freeze and came up with the design we wanted to build. We'll power up the burner. The burner's wiring is temporary for now, but we can run the burner and put some heat to it and see how it works.
So sometime back in 2012, a good friend of mine and co-founder of Thermalist, Dr. Professor Peter Hofbauer, told me I needed to quit my job, go to the basement of my house, and start a company called Thermalist, which is the development of the ultimate heat pump, natural gas-based air conditioner and heat pump technology. Heat pump technologies take advantage of two forms of heat. They take advantage of the chemical heat in the fuel, and they take care of energy that's stored in the environment. Everywhere outside there's heat. We can take heat from outside the house and put it inside the house. We burn 1 unit of fuel, and we can capture a partial unit of heat from outside. We can burn 1 unit of fuel and get 1.6 units of heat into the house. What that does is it's going to cut fuel consumption by up to 50%.
I must say that this particular project has really generated a lot of attention. I think that's partly because of the promise that it has to basically revolutionize home heating by using natural gas in a very efficient way. And also, the project itself has a lot of core technology, and it's a very natural link with the university. So there's been an awful lot of excitement that we've seen.
Okay, so.
Stony Brook had a satellite in Ann Arbor.
That's new. I think that's only been since last
I know
year.
exactly. Like we work within a block of there.
So I think Thurl just opened that office last year. So, like I said, there's some really whiz-bang stuff. The 3D printed car. Dr. Ahn, did you ride in it, or did you just take the video? You didn't get to drive the car? So there is a 3D printed car that fully functions. Yeah. Yeah, so it's been on the news a lot. Well, there's a video in a second. But it's been a great success, so let's watch the video.
Taking just 44 hours to assemble, this is the world's first 3D printed car, and it could soon become a regular feature in garages around the world.
We had a fabulous piece of machinery, and we had a fabulous team, and it really all worked just perfectly in the end, which is really fabulous.
Has only 49 printed cars in its body, compared with traditional cars, which have around 5,000 to 6,000.
This whole project has been one of the most exciting things I've ever gotten to do in my career. To be able to digitally manufacture a car is just a real good, it's a lot of fun.
It was unveiled at the International Manufacturing Technology Show in Chicago, Illinois, and its creators believe it could be widely available by 2016, or between 10 and 20,000 pounds.
Originally thinking that handful of people really people that actually contributed one of those hundred of people did not step up, we wouldn't have had this success here.
The finished electric car, which was built and designed by a number of businesses, can reach up to 40 miles per hour and can travel over 120 miles on a single charge, but as yet is not allowed on motorways.
So, like I said, that was unveiled at IMTS in September, and it's gotten a lot of publicity. They were on the Day show. They got a breakthrough award for popular mechanics last December when they do their awards. So it's a really cool technology. I believe it's primarily funded out of the Department of Energy. They're looking at how you can do this with light-weighted metals. But they've made a big investment in additive manufacturing, which is 3D printing more metallics. They used fused deposition modeling on a big area additive manufacturing printer, so BAM. The idea is that a lot of the parts that have been printed with 3D manufacturing or 3D printing are smaller, and this is the first time they're going to do something this large. They use carbon fiber reinforced polymers. The mechanical components, so batteries, motors, wiring, suspension, those are not 3D printed. You know, he said it was like 95% 3D printed. Well, the motor is not printed. I don't think that it's even that much. So it's mostly the body. The seats aren't printed. The steering wheel, the tires are not printed. And they did say it took 44 hours to print, but then it also takes a day to mill and 2 days to assemble. So it's not exactly as whiz-bang as they say. And some of you may have seen there was a Shelby Cobra as well that was 3D printed, and it's smooth. So that's the difference between this car and the Cobra, is that it's got like you can paint it, it's got that smooth finish. They didn't bring that one to the show, they only brought this one by Local Motors. And the company just, I think at the same time, they announced that at National Harbor, Maryland, which is where this convention took place, they're going to open a manufacturing facility there. And the other one's in Knoxville, because they're so closely affiliated with Oak Ridge National Lab. And then the other company that's been working on this is Cincinnati Incorporated. That guy in the red shirt was from Cincinnati Incorporated. So those are the three big people working on that. And then the last thing I'm going to talk about is this hybrid. This is like the largest hybrid I've ever seen.
This is not 3D printed.
No, this is not 3D printed. This is made by Oshkosh, which does a lot of military vehicles, which apparently if you search for military vehicles, they're all over it. This is a medium tactical vehicle replacement, and it is a hybrid defense vehicle. It's got onboard power as well. It's a diesel-electric drivetrain, and the idea is that the power can be exported. So this kind of reduces the amount of support vehicles they'll need to bring with them, or the trailer generators. So when it's stationary, it can provide 120 kilowatts of power, and when it's on the move, it can do 21 kilowatts of power. So the idea is they can have some of their radar systems on here, some of their satellites, whatever they need, they can just have it. And at first, it was just cool that it was such a big hybrid that they brought in. I mean, these people are tall; they're not like short men. So it's kind of intimidating to just walk up to this place, but. Those are some ones I found, and now Tim is going to talk about some of the other technologies.
We'll talk about a few of the other things. Some of these are a little earlier stage, so they don't have as much detail to them. I'll be back later to talk about Lawrence Berkeley National Lab as well. So this is speaking of local companies or New York-based companies, Superpower is a New York, Schenectady-based New York company, and the wire is actually made here in New York State. This works at liquid nitrogen temperatures, so about 77 Kelvin, and so some opportunities in terms of data centers that we're going to be talking about in terms of managing, particularly with DC power systems and lower voltages having very high currents. You can tend to have a lot of losses, but if you have a superconducting material, you can have a lot less, both higher performance and less material to carry the same current as other materials. I think these are some examples of between 100 and 200 amp conductors in terms of usually about 10 times less surface area for a given current carrying task. But they're here in New York, and looking forward to further relationship with them. HARP, which is Xerox's R&D group, is that correct? Thank you. Yeah, exactly. So this is interesting for the folks on this floor, actually, in terms of resiliency and environmental resource management. one of the things I found out was I hadn't like thought about this, but there's a wide variety. I knew there were wide varieties of aluminum alloys, but I hadn't thought of what happens if you take them all and throw them in a big bin and mix them up and decide to try to recycle them. You can't in terms because some will have a lot of zinc, some will have silicon, some will have copper, some won't. If you just melt them all down, you basically make low-grade aluminum or scrap. So this is actually an electrochemical method of detecting and scanning what is in what metals you have after they've come back from shredding or from a landfill, and then you can sort these and provide a higher value recycling stream. And so the actual value, this is an earlier concept where they're going to sort of impinge and pierce it and penetrate it and then use a little membrane. They have a little gun on display that for whatever reason, we couldn't find the pictures of this. So you have to take a little wand, you stick it on the metal and it tells you what it is. Then they have higher throughput automated versions where you can have sort several tons per hour. These concepts for those. So a neat way of managing this. Sun polling is, I think last year we talked about Other Lab. Neat group that does a lot of interesting, this is not their only ARPA-E project, let's put it that way. The idea here is solar cell costs have gone down noticeably. So a bulk of the cost is the balance of plant. So that's one of the driving costs. There's been other federal funding opportunities out there in terms of driving down balance of plant associated with solar installations. They were tackling solar tracking, and what they're doing it with, from the start they said, let's do this and try to figure out a way to do this cheaply. So what they're doing is making solar tracking devices based on the same technology that makes plastic water bottles. And so we don't have any in the room. Like, I don't see any in here, and that's like it's the unwritten policy, I think, that do not bring your thin plastic water bottles in the CUE. But that same blow molding technology they're using to make these little flexible articulating devices here, so that by using air pressure, they're pneumatically actuated, they'll pivot and move, but they come off, they're designing it from the start, engineering it so that it's all the same blow mold type lines and has the same corrugated function, so that it will pivot and move small solar panels. They actually had some big ones this year. Last year they were showing with tiny little squares, and they'd all do this little articulated dancing thing, but now they're actually looking at scaling up a little bit larger to look at more standard-sized solar PV panels. So, Heliotrope, also affiliated with, we're going to talk about Lawrence Berkeley National Labs after James and Ryan had a talk. Also based in the Berkeley area, Oakland area. One of the things you'll see over the next couple of months on the third floor of this building, we'll be taking out our existing Echo windows and putting in some Sage electrochromic windows. And so those have the advantage that you can dynamically change them on command and you can dim them. But unfortunately, when you dim them in the wintertime, you're also blocking some of the heat. And it heats that's transferring into the building. So when it's cold outdoors and it's 10 below or 5 below, whatever it is, ideally you'd like to block the glare but allow the heat to come through. And so they're working on material sets to allow that. That'll actually allow solar, you can have a choice. You can allow light and heat through. Say you want to do daylighting and heating of your room in the wintertime. Or in the summertime, you could do daylighting and block the heat. Or in the summertime, you could do, maybe if it's too bright for you as well. So you the light coming in and also block heat entering the room. So pretty fascinating technology. And then in more close to our Amtech group of folks, looking at another air liquid desk and air conditioner. So you may recall, we have desk type heat and refrigeration group, affiliated with Tatum Engineering, and I just forgot their name. SyracuseCoE, thank you. So they continue to be interested in desk and based systems. They're planning to find the ability to work with sources of 130 and 60 Fahrenheit water for heat and cooling systems. Gwen is another interesting one in terms of doing solar focusing or photovoltaic without actually having to move or track. So they're looking at ways of doing lensing embedded in layers and then taking advantage of fairly high-speed manufacturing as opposed to having to do big mechanical tracking systems, taking advantage of basically passive, inactive focusing so that if you have a system that can sort of kind of get it in the right general direction, it doesn't require precision tracking at all. So it's a lot easier, a lot faster systems, and of course cheaper ways to do it. And then Pacific Northwest National Labs, They've done exercises, for whatever reason they aren't available, but with military actions in terms of having these coupled up with gensets to provide refrigeration cooling to forward operating bases. And so again, this is a fairly high efficient way of turning using metal organic frameworks in absorption chillers to provide cooling from gensets. And that's military runs on diesel fuel, so there'll be generators all over different locations, so they can take advantage of small 5, 10, 20, 50 kW gensets of different sizes to provide also an air conditioning or cooling source to soldiers. This is really still fascinating. I'm trying to figure out how this works. I mean, man, I get how it works, but this was a darling, if you will, and there were plenty of videos on screen. I should pull this one, I suppose. But the idea is that you are able to cool or reject heat from the surface into the void of space, where you have an average background temperature is 3K. Is that right? Roughly. So when solar radiation strikes a building, of course you can paint your roof white, okay, reflect it. You can mirror it, it will reflect the light. What this does is it has the ability to actually reject heat from the building into space, even though the ambient temperature was to an ambient temperature within, let's see, 70 degrees, I think, the difference. So in other words, they can reject, if you have a surface that is 90 Fahrenheit and the air was 90 Fahrenheit, you're still rejecting into space. But more realistically, I think this is a better number to consider. They can reject 100 watts per square meter. And if you look at a single-family house, you can cover 10% of the roof and achieve 35% of the air conditioning, as opposed to actually cooling, you just be rejecting or radiating in space. So we're looking forward to seeing more of that. Now a video to show this one. Brown University is thinking about Dr. Melissa Green, some of her work in the water channel here at the COE. This is an example. Rather than having, I think if you've seen any GE commercials recently, you may see the horizontal sort of rotating water turbines in a river, and you see the stories about imagination and water goes into things. So this is another type of tidal power system, but rather than having a rotating propeller, it's actually an oscillating fin. And so if you've seen maybe you've seen a few videos of we've had whale fins and other things in the water channels upstairs. This is an example of a little different approach. So what I'm going to do is skip forward on some of these. We'll talk about resource. Okay, so water is 1,000 times, roughly 1,000 times denser than air, so you can have significant more resource, tremendous energy resource in terms of tidal power. Collaboration between Brown University and Georgia Institute of Technology as well. Let's get to the animation. So you don't want to chop up dolphins, obviously. So you think bird strikes are bad for bad press. A dolphin strike is probably even worse for press. And you don't want to have your device be smashed on a boat, and you have shallow channels out there where the propeller may not be applicable. So what they developed was a retractable device that can basically, could be airfoil. You imagine a wing, an airplane as you pitch down, or basically if you just driving around in a car, you just stick your hand out in the wind. If you pitch up, your arm moves up. If you pitch down, you go down. Same kind of concepts, but they have two blades in the water channel that work opposed to each other, and then just change pitch depending on where they are relative to their area in the cycle. Slower speed, so if the fish is moving along in the water, there's less likelihood of getting struck or hit or damaged. It also stows. You can fold flat. That's the concept. So it gets out of the way if you have shipping traffic coming overhead, or if you have a whale coming through, perhaps, then you may be detected, or if you have other animals. Yeah, let's see.
Whales are intelligent. They should avoid this.
They should avoid it. That is true. Perhaps a few dumber fish out there that every much preserved.
They limit them.
Yeah, that's right. Yeah. Of course, I suppose you have the gates closed, and maybe that's why I don't have them completely passive without coverage. But yeah, we get to that. Let's skip forward to the next one.
Physically, how big are those? Those per 100 kilowatt?
Yeah, that's a great. I don't know. I don't have the answer to that. So I have to check and go look and see if there's not. I can see the links for it. So. But Brown University and I forgot the name of the. Let's see if they have anything here about that. Nope, they don't have it on here. But more stuff on their website. I can check it out. So, oscillating hydroform. Oh, that's some nice stuff. Okay, let's get past that. Come on. Yeah, not yet. There we go. So another thing, Chetna mentioned before that in the case that they weren't printing electric motors in that additive manufactured car. So yeah, searched UTRC has some great, really nice posters, but I couldn't find them. I couldn't get them downloaded. But anyhow, the point being, they are in fact looking at ways of reducing rare earth metal usage in motors and looking at ways of additive manufacturing, printing side-by-side printing of copper materials and ceramic materials, and then having the ability to fine-tune your motor manufacturing, fine-tune motor size, capacity, and features. Collaborating with the Connecticut Center for Advanced Technologies. Another system that, let's see, Larry or Mike Wetzel in the room here. They worked with a group called Orgenics on it's actually a CAP award, Commercialization Systems, so CAP project through us as well as Senate CEO, looking at metal hydride air conditioning systems. This is a different take on that. This is looking at power generation where you have two chambers, a warm side and a hot side, and as the heat source drives the hydrogen from one side to another, you capture the energy and transfer it into electricity through an expander. And so they're around last year. They made some significant progress through this year. And then finally, one of the other things they're looking at is transportation and transportation modes, alternative fueling vehicles with natural gas. And so looking at addressing the issue of refueling, deploying up to 600 natural gas refueling stations in the U.S., one solution would have home refueling. And so they're looking at driving, as Chetna mentioned, one of the things that the focus of ARPA-E is driving costs down, making things commercially viable. So they're looking at ways of reducing the cost and increasing the efficiency of gas compressors and natural gas compressors so that everyone can have a natural gas powered car and have the ability to refuel it. And then another example of looking at CO2 condensing systems. The particular advantage they're claiming is in terms of ability to reject heat to very high ambient temperatures. Let's skip forward this one. And I'll be back shortly to talk about Lawrence Berkeley National Labs. Ryan or James, who's up first?
James, go first.
Okay.
I guess I'm being volunteered to go first. I don't have any slides, I apologize, but I didn't really have many pictures. So I thought I'd just, I had my list of what I wanted to say to make sure it was good. For those of you I don't know in the room, I'm James Shomar. I'm the CEO of Solstice Power. We're one of the startup partners here at the Syracuse Center of Excellence, and we're part of the ARPAE cluster. And we're developing a high-efficiency solar panel system. It's 3 times the electrical efficiency of conventional flat panels and provides electricity and heat from one system. So we were lucky enough to go with the Center of Excellence ARPA-E, but I was also part of the Nexus New York program, which is a NYSERDA-funded program. And that kind of takes green startups like us. I run them through a sort of lean startup model to try to get them to market. And part of that is to do some customer discovery interviews and market research type interviews. So a big part of my interest in going there was to learn more about CPV type technologies that are out there right now. Just because the traditional CPV model has been dying off a lot, and so it's the startups that have really been trying to carry that up. And so it's great. I got about 11 different interviews done at here. And one of the biggest things I noticed was looking at some of the ARPA-E proposals that they had. And the first was a spectral splitting CPVT, so that's concentrated photovoltaic thermal systems. So the idea there was basically you find some interesting way of splitting off the visible light spectrum away from non-visible light so you can capture visible with traditional solar cells and not visible with heat. These are all looking at mirror trough type systems. So Arizona State had an interesting one where they basically took an off-the-shelf filter from 3M that would allow visible light to pass through but reflect infrared. And so on the trough, underneath that filter, they had silicon cells, just like you'd see in a normal flat panel, and everything else was going to just a normal like heat tube. So that was kind of interesting. Gas Technologies Institute similarly reflected everything to where you have a normal the tube, but on the bottom side of that was transparent. The top side of it was lined with thin film photovoltaic cells. So everything light would pass through, and then the rest of it would capture heat. The Sharp Labs would direct everything to that to redirect the visible light back down to the center of the trough where they would have solar cells. So it's kind of some interesting ideas that were coming out. None of them have been gone beyond lab, really, in some small prototypes, and all of them want to license it, so I'm not really sure how that'll end up being commercially available, but that was interesting. Also interesting on my end were very high temperature multi-junction solar cells. So if you're not familiar with multi-junction solar cell technology, the idea is basically you have a layered solar cell that can absorb, each layer absorbing a different part of the light spectrum, so you get higher efficiency. And as what we're trying to solve, traditional concentrated photovoltaics, heat is a huge problem, so they're trying to find ways of high efficiency solar cells that can also withstand high temperatures. So I spoke to a few different, I think there's 2 or 3 there that were part of this, and they achieved 26% efficiency solar cells at 400 degrees centigrade. So it was quite impressive that they've been able to achieve that kind of level. Again, a lot of lab stuff that had much further commercialization potential. That was the majority of the actual solar technologies that were there. There were some outliers like Lockheed Martin that tried to evolve that. I was kind of surprised by that. The other thing I found interesting was there was a lot of speakers within the solar industry talking a little bit about the economics nowadays, which are kind of up in the air, particularly now that after 2016, we're not sure where the federal tax credits will end up being. So it was interesting to learn from, I think they had the CEO of Sun Edison as well as Solar City there talking a little bit about their perspectives and integrating distributed generation within utilities. So kind of disrupting their business model that they've been unhappy about for, God, a century or more now. So how do you manage that? So I remember his name is from Sun Edison there, but he was talking about how. No, from Sun Edison there. What's his name? I can't remember. I'm blanking. So anyway, he had an interesting perspective of saying that I'd like to see incentives.
No, he wasn't there.
No, I can't remember his name. But he was talking about I'd like to see incentives essentially to be to have a fair game, because right now when you buy solar, the incentives are right in front of you. When you buy gas at the pump or something of that nature, incentives usually tend to be on more of the back end through tax credits on their end or research development, stuff like that. That was one of the big things that came out of there. Also, dealing with distributed generation, you can see there's a stark contrast between utilities that are really trying to find ways of keeping their business alive in that type of model where you have more increased distributed generation versus those who are just trying to fight it tooth and nail. So there are areas like in Arizona now where utilities have actually lowered their supply prices and increased things like demand and more fixed expenses, purely so people aren't adopting things like solar or whatever, which really only flex. You have to compare with your supply. But you have other models where people are actually looking to finance distributed generation. You have people who are really looking for interesting ways of dealing with demand swings. So in California, that's now a big thing. They have the duck chart. I don't know if you guys have ever seen that. So that was really intriguing. Trying to find new business models to manage those two, to really deal with those, because those huge swings that you end up getting with a lot of these technologies, particularly renewable technologies. So that was my experience, sort of in a nutshell. Nothing too fancy, but feel free to reach out to me afterwards if you have any questions.
So how do you think you're going to take your knowledge and improve your company?
One of the intriguing things that I really liked coming out of that was that last piece what I was talking about in terms of integrating with the grid. And to back up a little bit there, because our technology uses a dual-axis tracker, has a little bit more of a flat production curve. It's a little nicer for a utility grid to deal with. So we've been trying to look at interesting models that if we were to say, own that system, that we could purposefully taper down our power production towards the end of the day so you don't have massive spikes, and seeing how that could help maybe mitigate demand flows and things of that nature. So that was really intriguing to me, as was getting a better idea of, you can almost say, competing technologies out there and those types of teams, what they're looking at in business models, that sort of thing. So it was extremely helpful to that regard. Thank you. And thank you for allowing me to come to you guys. You're up, right? Yeah, no problem.
Oh, yeah. I think it's on the slide.
Yeah, introduce. Oh, okay. There's a slide.
There's a slide. Oh, okay. All right. So, so my name is Ryan Falkenstein-Smith. I work in the Combustion Energy Research Lab, which I'm actually going to talk about in the next slide. That's located here at the Center of Excellence on the first floor. So I'm just going to kind of offer a student's perspective. I'm a PhD student at Syracuse University in the Department of Mechanical and Aerospace Engineering. So when we went to ARPA-E Summit, as a researcher, it's a little different because you see all of these different technologies that are showcased, and as a researcher, you're doing a lot of fundamental work. So the technology showcase was showing breakthrough technologies and tangible innovations, and decision makers that were very interested in certain investments. It also gave a wide, very interesting view on entrepreneurial spirits, particularly in renewable energies. So, coming from the Combustion Energy Research Lab, our lab, just background knowledge, our lab is fully equipped. We mainly deal with fabrication of solid oxide fuel cell technologies, focusing on characterization, testing, and integration and implementation of SOFCs, power generation devices. We have a number of projects that are NSF funded as well as AMTEC funded. One of the things that I wanted to look at, or one of the things that I saw, is when we were at ARPA-E, the technologies that we develop or the things that we work on are not just fundamental research. It's that fine line between practical application and fundamentals. And not every engineering PhD student, not every engineering researcher can say that. So we really looked at fine lines. And going to ARPA-E was an eye-opening experience of saying, oh, hey, look at all this technology that's being developed. How does that apply to our lab? So one of the things that we started looking at, or one of the things that Ryan and Dr. Ahn and I started seeing, was further studying and innovative ideas. So there was many different ways. One of the big problems that we actually have to overcome a lot in our lab is processing. And what I mean by that is fabrication processing. How can we get better power out of a fuel cell technology? Or how can we get better power? What's the different way we're designing this ceramic material? So we got to see catalyst development. So here's a poster. It's not the best picture, but the gist of it was they were using a different type of spray breakdown so that you could apply a thinner amount of catalyst layer onto an SOFC material. So therefore, you're getting a more power out of a lower temperature. We connected with a bunch of other researchers from around the globe, mainly Georgia Tech was working on some things, Redox was working on similar stuff. And we are also there to showcase the COE and represent our lab. If you haven't been to our lab, I recommend that you stop by right after this because I have to go down there and work on a bunch of stuff. So these are the various connections that we were making, the people that we mainly talked to that really jumped out and seemed interested in what we were doing. There was a bunch of fuel cell technologies that were also being discussed there. But these guys I put on here because of the thing that I'm actually about to talk about. So one of the things that I think Chetna mentioned is that ARPA-E is not only focused on innovative technology development, they're also working on emission controls. And we develop all these great ideas, we develop all these innovative thoughts, but it really doesn't mean anything if it's not efficient, or does it mean anything if it's not really, improving emissions quality in any way. And one of the major discussions that was being had was carbon capture and storage. So this is one of the diagrams that basically talks about how plants are implemented now into an environment and then how not only they can operate, but capture and store carbon. The biggest questions now, though, are how do you capture it, and then how do you store it? So that was one of the major discussions that was being talked about. And the thing that really appealed to me was that's part of the work that I'm working on now as a PhD student. So I wanted to see the other technologies that were actually going on there, as well as, was my idea great? Well, how did my idea compare to all these other technologies? So The first one that I saw was technology centered alongside. It's a facility in Norway that basically takes large-scale carbon capture technologies and implements them into industrial factories to see if they're applicable or to see how they run. So right now they're working with two companies, Asker and Aker, both European companies, that basically use a solvent-based carbon capture solution so that it's a post-combustion process. So you're capturing carbon from a flue gas using a solvent. It's actually a pretty innovative idea. The facility is one of a kind. It's available to see commercially how is it possible to capture these emissions that are coming from these combustion processes. But again, it's a post-combustion process, meaning that it's happening after that. One of the actual ideas that's getting a lot of friction in the past couple of years is cryogenic carbon capture systems. So essentially what that's doing is it's taking flue gas, drying it, compressing it, and then from there it's cooling it, solidifying it, so that you're filtering out hydrogen sulfide and all these other contaminants there. And what you're left with is just CO2. And then from CO2 being cooled, you're actually having these little solid materials that you can actually store for other containers. But the biggest question that I had for them when I was talking to SES, which is Sustainable Energy Solutions, which I can give you more information actually if you're interested on that, was one of the big concerns is, okay, you can store all this carbon. What are you going to do with it? And that's a huge question because you have to have a demand for something like that, and that's one of these big discussion points. Yes, there is a major demand to reduce emissions, but you have to have something to do with all the CO2 that's building up. So it's a novel idea. There was another company that actually was talking during the carbon capture forum. I forget their name now, but maybe they were talking about just burying CO2, which is actually a popular opinion at this point. So it was then that I started talking to other companies, particularly the DOE, and they referred me to something, a project that Praxair was working on with OTM, which is oxygen transport membrane. So the one reason why I fell in love with this is because I was working on something very similar to here. So I was like, oh, great, I know what they're talking about. So essentially what's going on is that you have a ceramic membrane similar to an SOFC technology that is an oxygen transport membrane. So you see oxygen ionic transport that's going through here, it's reacting with that fuel, and therefore it can be used either to generate syngas or contain a carbon capture or contain a combustion process, and therefore you can contain a CO2 separation. So essentially you have a hollow fiber, you have this tube, you're running the fuel inside that tube, oxygen ions are transporting through it, and therefore your products can either be CO2 or H2O, or it can be syngas. And then from there you can compress it and then use it for other applications. So one thing that really jumped out at me is, one, it's not post-combustion processing. It's oxy-combustion processing. So then it can be integrated into current combustion processes. One of the major advantages of post-combustion, so the cryogenic processes and the Maytag thing that I was showing you before, is that they're talking about retrofitting. They're talking about retrofitting all these different factories, which is a great idea for a large scale, but what do you do for small scale? So Praxair, similar to ideas that we develop here in Comer, are talking about these OTM boiler systems, the processing heater for syngas. They're mainly focusing right now on syngas generation, which seems to be cut off. But essentially what you're doing is you're running your recycled fuel through there, and you're generating syngas from that, and you can recycle it over and over again. The similar practical idea can be applied to a boiler. So syngas fuel is burning in, oxygen from low pressure ambient air even, you can have the oxygen ions transported through it, and therefore you can have some combustion and steam generation processes, which then can go back through another oxygen transport membrane. So it was nice to see exactly how, this is me, but it was nice to see exactly that my work was actually being more in a practical sense, and it kind of validated what I was doing. It definitely gave me connections and ideas. I've been in contact with Praxair, and they're out of Buffalo, so I'm going to go meet with them and actually talk to them soon. So it was a great connection there. And it definitely kind of put me in the right direction of saying, hey, consider this idea. I mentioned about the ideas of actually finding a need for storage, finding a need for how does it compare to post-combustion processes and pre-combustion processes. So that's what I got out of ARPA-E. So any questions? Great. Thanks. I'll be after you. Thank you.
All right, so now we're going to talk a little about Lawrence Berkeley National Lab, and specifically Flex Lab. So last week I had a chance to visit both Flex Lab as well as the Center for the Built Environment at University of California at Berkeley, so we're going to talk a little about both. And there's a video for each one of these. I'm going to start out with first the Flex Lab one. So Flex Lab in Berkeley and has a...
I think there's this urban myth out there where people believe buildings who are highly energy efficient are not very comfortable for employees and users.
Even if you've got a beautifully designed building, a lot of the problem comes in the operational phase. Once you bring people in, you change the dynamics.
At Genentech, we're constantly innovating and following the science. So what we've done is we formed a partnership with the Flex Lab at the Lawrence Berkeley Laboratory to take that same approach of innovation and following the science and apply it around energy efficiency and building optimization. Environmental sustainability is part of our DNA, and if we take our combined knowledge and bring those resources together, we can make a big impact.
Flex Lab is a set of test beds that allows us to capture the realism of building performance in a way that we can do good science. We can understand the results, we can tease apart the details and understand what the causal factors are. Our first project, we had a great opportunity here to build a piece of the building that's being built in South San Francisco, bringing in the key elements of that building and trying to assemble them and see if they can operate as intended.
Scientifically, now we're able to really measure glare, heat gain, the entire building performance aspects, which we have never done before.
We pay attention to the big drivers, the big things that drive cooling loads, like the amount of glass, the type of glass you use, but also the important details about where sensors are located and how they're linked to each other, how people work in the space.
You can simulate a human in the space, and you can actually then see how it integrates with the glazing, with the lighting systems, with the electrical loads in the building. So you now actually can test it all together in a holistic perspective.
We can substitute in all kinds of wall systems, window systems, shade systems, lighting systems, HVAC systems. We can figure out what combinations work best under what conditions outside. We're going to try to solve problems in 600 square feet of Flex Lab and then apply it to the Genentech building at full scale.
It really gives us the scientific approach of assessing data, assessing building performance, and confirming what we typically have done just through simulations. And I think it's really like the handshake between science and architects.
Each day, our employees come to work to do.
So that's the idea. So what was there, you're going to see a lot of the, well, kind of tour of the new Flex Lab piece as well as their additional window test labs. And as you saw in the video, it really does spin. Actually, it rotates 270 degrees. So you can, if you have a window facade system or a building system or any kind of system you want to expose, whereas you went to a test facility that was not flexible like this, you would be making compromises or assumptions based on position relative to the sun. What you see here is a model of the actual facade system is going to be on those kind of model of the actual materials that are on a particular client's building. So they can install this, test it. The buildings are occupiable, so you can also do mannequins, you do simulations. You can also put humans inside them, much as you can here with the CUE and the TIEQ or other facilities, and test performance and look at actual experience in the environment. Looking at, so it's not only one building that rotates, and three larger segments, including a large high bay area in here that can protect. It needs to be wall off from each other, as you see here, or they can be opened up completely to make about 6,500 square feet of space. The two-story space here is already set up to allow you to put in a second story. So if you want to do multi-floors, you can do that as well. And you see this framework on the front is here to make it easy for you to install external light management devices. Let's say you want to install a shutter system. Let's say you want to install a secondary set of electronic blinds, for example. You can do that as well. In the overlap that you'll see later, they have some interesting ways of making this go up and down, go on very quickly. Let's see what we have. So here's an example looking into some of the lab spaces that we have. This is actually their older test facility up on the, further up on the hill. I must say that LB House on the hills are remote overlooking Berkeley. Building 90 here has a fantastic view of the bay and just a great, nice, extraordinary. We were kidding that you probably make a big dent in the national debt if you had to sell to a national lab. But significant capability for high definition thermal imaging, multiple variety of thermal sensing capabilities. And then you see over here, this is actually this particular electrochromic glass is Sage, and you can see the multi-segments that they have here. Not only for you can use them alone or couple them with other blinds and shades. One of the things they're doing ahead of time was we talked a lot about glass and facades and things of that sort. Actually, the lab is not just about glass. It includes HVAC systems, includes power monitoring systems, includes underfloor ventilation systems. It includes the ability to do overhead radiant panel systems. Essentially, any heating, cooling system that they could imagine at the time, there's hardware and infrastructure in place. So there are multiple redundant systems available for doing heating and cooling from any source. And along with that comes plug load monitoring and the ability to do power monitoring of the occupants and any of the systems that you have in the space. And this is an example of multi-level temperature monitoring. This is another example. This is on the rotating lab itself. And so you see the heating, ventilation, all the different mechanical systems, a large data closet for monitoring inside. Lots of flexibility in ducts. Somewhat, this is obviously kitted fairly tough, but this is not really very flexible. One thing to note we were asking about was actual use of extensive wood framing and steep, very big beams and close pitch. So remember, this is in a seismic zone, about 100 meters from a major fault in the area. So it's built to take a significant seismic hit. Lots of not real sexy photos, but the point being just kitting and wiring everywhere to redo, configure anything you want. Every building has at least this much in terms of plumbing for chilled water, hot water, various refrigerant systems, forced air systems, hydronic, or I don't think they have steam capabilities involved, but I remember that one for sure. This is an example of a high bay. They can do skylights, so they have pods already in place to pop out the roof in various different sections if you want to try those. A variety of the lights can be changed very quickly. High bay, another example. This part here, this is in the case. Most of them are mounted on the forward and back. Most of them are hard mounted pad, as you can see here. But this one, a little different in that it's built up on steel, and in the event that someone came in with a system or a brand new HVAC technology or heating system or something, GWIS idea, they can cut this free, hoist it all the way out of the way, and you can place your HVAC system here if you wanted to, or your heating ventilation, or whatever infrastructure you need to include. It's ready to go. Couple up. Yeah, we would show that one. And then this is messy, but for those of you who know anything about National Instruments equipment, this is a six-figure table in terms of what's on this. And this is just a small portion of the type of data collection that's in the space, both inside the room and outside the room. This is about 10 compact Rio 8-channel systems. No kidding, when they're fully populated, about $120,000, $150,000. So
it's on one of those foldable like.
Yeah, it was just quick. Moving along quickly. I should say they've done work. They've had customers in the rotating space, but a lot of the work in the main those blue buildings. So they're still doing calibration and background assessment of the facility. So they're still ramping it up, bringing it online. There's a tremendous amount of understanding the baseline is very important, obviously. So this is something that we're going to be maybe dealing with in about 18 months or 24 months up until TAQ. Something I caught my eye was the idea of planning ahead for moving your sprinklers around. So they actually have flex hoses connecting all their, so it's the flex sprinkler. Minor detail, but a lot of forethought in terms of how the big thing is. So long view, this is pleasant. Going for the view looking out over the bay. Yes, that's turkeys. There's some great turkey habitat for whatever reason. This is open.
Could be a turkey function.
Could be a turkey. So lots of nice turkeys, beautiful sites, nice locations in there. Again, just flexible everything. And then this is with their older facility. They've been doing electrochromic and blind testing. But it's thinking ahead, they go ahead and put in basically little winches and cranes so you can come in and run one test and then put in your other device in front of it, and then once you can bring it up as needed to drop it down as you need to. Compare the testing with the lines versus electrochromic lines. And then lots and lots and lots of weather monitoring equipment. It's a cluttered picture because it's a cluttered rack of gear with all kinds of indirect solar information, temperature, humidity, ability to change it. Okay, so the second visit of the week, and this relates in somewhat, I should say, the Center for the Built Environment does many, many other things, but one of the things they do is related to personal comfort systems, and had a chance to meet with Ed Ahrens, who's the director of the Center for the Built Environment, and this should be, if you Chetna mentioned the Delta Award that has received earlier in the year, and this wraps up some of the figure in terms of energy savings, in terms of percentage. So if we all, go ahead, sir. You're about to say something.
This is my work.
There we go. So this is on their right on their website.
We called it task ambient, so we said call it personal environmental control systems, so we adapted it and used it.
There we go. So he's taking it on. So talking about the energy savings.
You could have called it EDS.
Yeah. We need to figure out a COEPA acronym. The idea about the net personal nested environments, again, if we could all have a bubble or a small space around us that works represent our personal ideal conditions, for me would probably be about 67 and medium low humidity. The rest of the world could be 100 Fahrenheit, or it could be 10 degrees C all the time, and you'd only have to condition my bubble, and likewise for everyone else in the room. We wouldn't have to condition the rest of the building, we wouldn't have to condition the rest of any space we ever went to. And then what this gets at is that as you open up the envelope of your heating and cooling set point, you have opportunities for significant improvements in energy savings. As it shows here, if you start to lower the set point, you have opportunities for improved comfort in San Francisco, Duluth, and as you increase the cooling set points, you have opportunities for savings in Miami, San Francisco. And that's the essence of this ARPA-E, delivering efficient local thermal amenities. FOA opportunity that Chetna has many others here, also folks from SyracuseCoE and UTRC and Cornell. Air Innovations, thank you. Not SyracuseCoE, I'm thinking Bill Bush.
Bill Bush.
Yeah, that's right. Bill Bush are working on. And we're going to one last video. We're going to do this one the hard way. Pardon us if it turns into an ad for Marvel superheroes.
On the path to driving up the PG&E bill. Tonight, researchers at UC Berkeley may have found one. And as ABC 7 News reporter Jonathan Bloom explains, you don't have to leave the comfort of your office chair.
It looks like a chair, but the word chair isn't anywhere in its name. This is a personal comfort system.
We try to make something that looks like a regular desk chair, as you can see, but the difference is inside.
Hidden beneath the black upholstery are 3 silent fans, 2 heating coils, and a battery.
Yeah, I'm in heating mode here with the red light, and if I switch it over to cool, I get the blue light, and I'm immediately cooled. I can feel it instantly.
Dr. Ed Ahrens led the research at UC Berkeley's Center for the Built Environment. They studied all sorts of ways to keep workers happy and save energy at the same time.
This is a foot warmer.
From this to a 1-watt desk fan and a cooling pad for your wrists.
During the winter, we can turn this.
They found out heating and cooling people is a lot more efficient than heating and cooling a building.
In the library, we were able to cut the energy use by 50% during a period in which we gave people these chairs and kind of turned off the thermostat.
Researchers have been testing the chair out on real people here in this climate-controlled test chamber where it's a brisk 64 degrees right now. My nose was pretty chilly, but since I sat down, I completely forgot about it because the rest of me is toasty warm.
The responses are really positive.
With 30 test subjects, they brought the room down to a dry 62 degrees and up to a humid 86. Hardly any complaints. The key is giving people the power to do something about it.
When they have control, they always perceive that the environment is better.
There's also this. 2 people can have up to a 10-degree difference in the way they perceive temperature. Now, instead of arguing over the thermostat, they can both be comfortable.
We hope
that we are going to change the rules. We are going to change the way that people design for comfort.
They're already shopping for a manufacturer who will make the chair at UC Berkeley. Jonathan Bloom, ABC7 News.
Yeah, well, there it is. So I got a chance to sit in one of the chairs, and then I immediately wanted to buy one. Not for real. And there is a company, a startup company that's trying to move off and start selling some of these called Acutherm and personal comfort systems. The problem is that you have a battery that's on the chairs. There's a battery affiliated with this piece, or it has to be plugged in something, or there's a battery or a power cord connected to your foot warmer, or there's always this energy problem. So what we spent some time talking with them was about what they're doing with their Delta award, which is a magnetic resonant coupling for wireless power transmission. So they already have they already have a lot of the work that's invested in terms of the objects to warm persons at a personal level. We're looking at how to create a power environment so that you can just lose a valve and have them coupled without having to actually plug them into anything. Even the point of, you mentioned having like foot insoles in your shoes, that they put your foot down in the right spot. Of course, you have heat, the magnetic resonance that would heat foot. It's kind of cool. And then one of the other things, we got a chance to walk around. I apologize for the lighting. There's a lot of light in interesting ways that made it difficult for my camera to tolerate. But as one of the things Ed mentioned was the difference in temperature, you also had some issues. This building was really cold, about differences in human perception, the difference of what we feel versus how the building reacts. So these are little personal desktop weather stations, as they call them, called weather stations. But that also measure the radiant information about what's going on. So this would probably be a better interface between us and our radiant panels on our desks.
Did you bring them back?
Well, I'll ask him. I'll certainly ask him for one. Everything seems to be on its way somewhere. So I'll find out if we can get one of these. Or at least have to make one. So we'll get somebody to make one for us. A couple of the devices we're doing. He had a walk-around cart. Ed mentioned that the project that was done with the New York Times building in New York City, and when they were doing building actually occupancy. So we had a cart that measured temperature at different levels and airflow, those sorts of things. So they have a lot of those kits. This is a nice Cadillac SUV seat, I believe. For me, it's on the car seat. But looking at ways, when you get in these nice cars, you have the heated seats, you feel nice and warm. I asked them how that compared to their energy consumption in their car, their little seat. That's about a 10 or 20 to 1 factor of energy consumption. So not nearly as efficient in terms of what they're doing. And then we have thermal mannequins as well. That here she is, a multi-zone thermal mannequin used for simulation testing. This is the 1-watt whisper fan, as they call it, that they tested in the library. So the key thing was that it'd be quiet, imperceptible, and then and be allowed you to drop. Of course, they have a drier climate, less humidity, so you can get a little more, away with a little bit more. But a lot of things they fabricate with their digital printing, digital lab. A lot of their printing services they have on campus, and of course they expand out to do larger runs. That's a type of 3D printed material there. The hybrid chair, again. And then what I was just astounded by how many of these had. They had 30, 40, 50 of these ready to go into a test some location. So the battery will run about a week in cooling mode, about 3 days, 2.5 to 3 days of operation in heating mode. So but they're getting ready to roll these out and go somewhere.
The cooling mode, just airflow?
Just airflow. Just airflow. So no.
Which would not have qualified.
No, and they would not have qualified. The only way they got in was on the power coupling issue, dealing with coupling these other devices. And they had trouble getting well into the ARPA-E qualification. They struggled with their economic model as well in terms of meeting $60 deployed. Same challenges you predicted in terms of do you pay for the chair or do you not pay for the chair. So that's exactly what you're talking about. Foot warmers. This is it looks like you're going to an easy bake, getting toasted, or like a foot broiler. That's an artifact in my camera. Although there's a psychological factor of what color of bulbs you actually put in these things. That goes into the mix as well. And an unintended consequence of the ban on certain incandescent bulbs, you started banning incandescent bulbs, and said you can no longer get his bulb because of this particular ban or something to that effect. So he's having to source new bulbs to do this function.
I think he uses less than 60 watts in the
I don't know. Some regulatory thing, but the point is your usual heaters would be 500 watts, 800 watts, something like that. This is about 40 or 80 watt, foot warmer.
So it has to be repackaged. It can't be called a light bulb. It should be called a thermal heat device. That gives out a byproduct.
It's like my new engineering hire question was how efficient is a light bulb, and it's like 4 or 6%, something like that. So the rest is heat. That's great. That's what he wanted. But and then one of the last things about the facility, some interesting wind tunnel models in there. This is a model of a particular, I think, a military facility. So they use it down here, something like that. But anyway, looking at will a building be comfortable with passive or just natural ventilation or heating, with ceiling fans location, what do you need? But anyway, the ability to test those and put things, so interesting facilities. Yeah, so that's my trip report in addition to our what I did with my week. Questions about anything? Yes.
The electronic work was Steve Circuits.
It is Steve Circuits. Yes. Yeah.
They'll show you the panel where they blow an argon in it and they can do something and change from opaque to. Wasn't the lab? It was one up over here.
No, it's down the left. Is that the Pella window project where they have the multi-gases?
Yeah, they have the blow an argon and they're doing something to it. It goes from opaque to transparent.
I've seen. Oh, there's one. Actually, is that building technology office work that was with? They had. I'm trying to think what they're doing. They had one that was. No, but think about. Sorry, I didn't see that, but I'm thinking about another one which was automatically responsive to temperatures where it would expand or contract. They're using elastic materials to affect dimming and shading without any kind of external input. So I didn't see that.
But Chetna, James, Ryan.
Firing
line.
Yes. Yeah.
I was going to actually ask you a question. I was wondering if there's anything that you learned that you're planning to implement here or bring back.
So I learned some things. I want to get some of those heliotrope windows at some point. I would love to demo some of those things. Some of the features that they're using to speed, exchange of window systems out. I don't know that we can stick those on our common air system, but maybe other locations that we can. And then I actually learned a lot about how you create maybe I should have known this, but the background didn't, in terms of creating isothermal zones so that you can the only change in heat or energy in the system is based on inputs and outputs. So sort of yes, but I can't give you a perfect example.
Tim mentioned in passing, I asked you to talk about the electrochromatic glass that we're going to install.
Right, so we're going to be right now, it's the last Friday, we have shipped from Sage Glass and was 5 sections of windows. So if you look up there and you see the shade windows, they're about 4 feet by 6 or 8, whatever they are. Those are going to be taken out of the 3rd floor on the west end of the building. So we're going to take those out and put in replacements in the form of electrochromic glass, and they will have zones. They have 3 zones: a bottom, middle, and a top zone, which will then be used as part of a study collaboration with Siemens Corporation to look at occupant comfort, thermal load on the environment, and daylighting. So ways of optimizing control strategies for all 3. People being happy, allowing the most amount of daylighting and heat to the system or heat blocking as possible. And then that'll be compared with the control space on the 5th floor where we will retain the existing interstitial blinds. And so in the next month or so, we should be installing those windows, wind allowing. Temperature apparently is not the issue so much, but it's having a good stretch of wind without precipitation, calm wind, without excessive precipitation, what we're really waiting for.
Tim,
yes, sir.
Is the electrochromic glass part of Eric Schiff's program or not?
It is not.
Have you spoken with Eric Schiff about the electrochromic?
I have.
We've mentioned it to him when he visited us that we're doing the project, sure. Yeah.
Yeah, they're taking some of the ideas from that, but it's probably not as applicable.
Are those 3 sections fixed?
No, they're all adjustable independently. So you can have, for example, you want privacy, but you want daylighting. and you were on the street level, you could dim the lower level, and then you could have the F1s line up, or you could allow go.
So I think, you mean they're fixed like at the factory? You know, there's 3 zones on the window.
Right.
And they were, I mean, it's wired, right?
It's wired,
It's
yeah.
electromagnetic, so it's,
There's 3, and they're right. They aren't, you can't move up, but once they're engineered in and built in, they're not, they can't move. The opaqueness changes from 5% to 95%.
And what about the cost? Is any progress made on the cost?
No. Don't really know personally.
so this is beyond our, so this is an experiment.
We're not. This is a collaboration between Sage and Siemens and us. So in terms of cost, it's basically a donation through Sage to the project and so parties together. So I'm not seeing the cost of the one.
It was interesting to see the statistics on the funding from the universities make up about 5%, and the second is small businesses. So what was your impression that you speak to people from the university? How do they balance this very applied direction of ARPA-E with the need for fundamental research? Because one of the criteria is that it should be high risk. It should be high risk in terms of technology, not even high risk in terms of fundamental research. Did you have any conversation about how universities manage the mission to drive the frontiers of knowledge, and the mission to come out with a product, and they're getting a higher chunk of the money?
Not this time, we didn't talk about it, but generally, I've talked to universities about this generally. It does tend to be almost all engineering departments. You don't see as many chemistry or physics departments. And it is that subset of engineering faculty who are looking at the applied projects. Now, that's usually what the PI does, but for example, they have somebody who does more fundamental research on some of the more early edge research ideas. So, what they're looking for is partnerships, so they want to balance that basic or more applied research with the transition. So you'll see it's a 3-year project. It's mostly university in the beginning, and then it kind of moves towards the company end by the 3rd year. I agree with you that it is a divide where they're not, it doesn't meet the mission of fundamental research. But I think they've found that there are enough people who are interested in it that it's been good. And there are some universities that have made a strategic interest in ARPA-E. So, for example, I've talked to people at Case Western, and they have brainstorming sessions with people in all of the departments. They all come together, and they decide that it's not just engineering, it's physics and chemistry and biology. They all come together and come up with ideas. So you'll see very diverse teams there. And it is because the universities made a strategic interest in energy, and this is what they see as the best way to do it.
Yeah, it would be interesting to know the concentration of these universities nationally.
Actually, some of the top universities do this.
Yes, so that's the point I'm making. That you talked about the strategic alignment with universities actually. So you would have to have the base to pursue conduct like that, and you end up seeing that 55% maybe the universities are the same universities.
Yeah, I mean, it's MIT has the most number of programs,
yes.
And they think it's Caltech, and Georgia Tech, Case Western, Florida, Arizona State. I'm sorry?
PGRI is working with China.
Georgia Tech. Georgia Tech. Yeah, they do a lot.
Known as the Research Institute of the University itself.
Most of them are through the Research Institute, actually.
Yeah.
I think they funnel most of them
But I don't think it's true that universities are only about fundamental research, especially in engineering. A very large chunk of the research money at the universities, maybe the majority of it, is not fundamental research.
I think the discussion among the researchers that the ARPA-E program is aligned with the politician short time frame of elections and things like that. So they're not sure how they come into the picture.
It's changed the culture of DOE. So I think DOE had a reputation. And you know, there was a vision of actually doing something that would speed up the cycle within DOE. And I think we're seeing it now in the base DOE programs, and an approach that's similar to what ARPA-E pioneered.
I was going to say, I'm not so sure you can draw a parallel with IARPA, DARPA, and ARPA-E, but this would go back to Ez's comment here is, in those worlds, it's very common for universities to be playing a role in both 6.1 and 6.2, which basic and fundamental as well as the applied research.
Okay. And even the National Science Foundation, one of the biggest programs is the Engineering Research Center,
yeah.
which has a very large, it's mostly an applied component, not fundamental. It has a fundamental component, but the majority of it is applied.
So going back
The nice thing is there's room for both with these programs.
Going back to your comment about DARPA, one of the things they've struggled with is with DARPA programs, they have a customer. The customer is the Department of Defense. They imagined ARPA-E would be like DARPA, except who's the customer? Who's going to buy the stuff?
But to that comment, Chetna, that goes against them just as much as it goes for them. Because often they have a customer on paper. But they don't always have the customer when they're playing the bleeding edge.
Yeah.
They're way in front of the customer. So I mean, there's that too.
So I'll give James the question that he asked him. So, is there anything you saw that's going to change what you're doing?
We're looking a lot more into the grid integration ideas. So one of the also side effects of that sort of Nexus program we are in is customer interviews. So we've been looking a lot with universities, with sort of like craft breweries and distilleries, hotel chains, restaurant chains, some of the ideas that we've been throwing around. And particularly in like, usually the bigger you are, the bigger demand becomes an issue. And trying to look at like integrated demand side management softwares and things of that nature, that would be very complementary to what we're doing, and perhaps even a nice bridge in the market, considering it's taking a while for, it's a long process to develop a product and actually get it into the market. We talk about scaling it up and going through commercialization and all that sort of stuff. That's a long process for an established company, let alone a startup. So that was one thing that was really intriguing to me, because I don't know, it's sort of the 21st century of the utility grid, essentially, is the way I kind of perceive that. So what are some intriguing ways that we can try and involve? The downside of that is that's, you know, solar itself, there's been a lot of big players, but a lot of people have kind of dropped out of that, whereas that side of it, you have GE and Siemens and all really, really big guys who are interested in that. Some tied to the old system, some kind of innovate. But that's, yeah.
Do you have any use for the solar tracker that I saw on the slide?
Yeah, I actually tried to reach out to them because that was really intriguing to me too. I forgot to mention that. Yeah, we were looking at that. I also wanted to check out, I wanted to get the information about the desk-based AC system. Yeah. That could be potentially complementary as well, just to throw some heat into that. So yeah, I'm trying to look into some unfolding too, particularly for like a cheap system. So we're also looking at like food trucks that might, you know, they're required by the health department to have a hot water tank, and you know they're using gas generators and that kind of stuff. So it's going to be kind of a neat little application, and then you can get those systems kind of lightweight to run the truck. So just some ideas of
the field testing trip to Southern California, probably food trucks.
Yeah, exactly, right? Yeah, just another, yeah, that has no motivation whatsoever. Yes?
It's a question for Ryan. But the carbon capture and sequestration, you mentioned two of them. One of them, the companies is solar. One of them is trying to absorb CO2 in some sort of a chemical.
Yeah,
what do you do with this chemical? If I go absorb the CO2 from a 1,000 megawatt power plant, what do I do with all this chemical?
I mean, that's part of the discussion that they're talking about now is what are you going to do with it after you're done capturing it, or what are you going to do with all the solvent? So I think from what I read, a website really didn't give that much, or when they talked to them, they didn't really give that much about what they do with the solvent after. But for the most part, that's one of the big discussion points that we're talking about right now is what are you doing with stuff? How are you storing it?
Even with this idea of refrigerating it and freezing it into dry ice, First of all, you're going to use a lot of energy to do this. Okay? Do people actually account for the energy cost of this process?
They're trying to justify it. So one of the big things, that was one of the questions when they had the carbon capture forum is, okay, how much energy costs? So somebody was working on it. Do you remember? Do you remember who? Oh, not you. Sorry. Someone was working on it. They're trying to justify the numbers. But there was a chart, and Ryan and I, when we were talking to SDS about it, we're just like, for the compressor and running through the turbine, it's a lot. So they're trying to justify it now.
It's even worse if you're trying to freeze it.
Exactly. Yeah. So it fuels my research.
Quick comment too, I remember from one of the discussions they were talking about essentially the need for carbon tax in order for that to also be economically incentivized for that. So that's a big thing that's going on in Europe right now, but we don't see that here in the U.S. But I remember them mentioning that who's going to implement this unless they have that financial incentive to do so, unless there's some sort of regulatory.
So one of the main focuses now is producing or capturing CO2 for enhanced oil refineries or enhanced oil recovery systems. So taking that technology.
CO2 inject on the ground?
Yeah. So they're trying to, somebody was working on trying to create some CO2 capturing system with that.
This is an alternate to hydrofracking, so this would be CO2 fracking?
What is it? It's using CO2 and shoving it underground, and then oil is basically coming back up.
It's to push the oil out of tight pores.
Right.
Tight combinations.
I've heard instances where they're trying to do the reverse, where like after they've taken the gas from hydrofracking, then filling the well with CO2. Have you heard of anything?
Yeah, I've heard some stuff like that. But that's the whole point, is you're trying to find this niche of where this technology fits. So you have all this stuff stored, where does it go? That's one of the biggest discussions happening now. Yeah. There's not really a technology that's the forefront of all this, so there's a huge market out there for carbon capture technology.
I think it's reflective of one of the other areas of ARPAE is funded in terms of synthetic photosynthesis or augmented photosynthesis or accelerated photosynthesis methods. So you capture it in the form of, other longer chain carbon molecules, long molecules. They can store that, easier to store that, and then it's CO2 gas.
Yeah, ASU was working on something like that. So, but I mean, in terms of large scale, that's the same. In me, at least, when they had the forum, it was the major focus.
Oh yeah. Well, I'm just saying that's an early stage.
Right.
As well as UC San Diego.
Yeah.
Thank the panel. Thank you all for coming. And outside that door, I trust there are some refreshments, so come and join us for individual conversation and refreshments. And then Ryan invited you to come down to the lab.
Oh yeah. Stop on by.